My name is René Schmidt. I'm going to talk about storage and storage at Uber, and particularly about how you build big scalable storage systems. This is some work that we have been doing over the last almost 3 years, 2.5 years plus, in Denmark, in Aarhus, or actually not here, but in Aarhus. So in case you're not from Denmark, we have an Uber office in Aarhus. And Uber is, as you know, a global company where we do rides across the world, and the engineering organization is actually also distributed across the world. So we have offices in Denmark, we have offices in Bulgaria, and a bunch of places in the US too. And for myself, so I worked there for about 3 years, primarily on storage. Before that, I have worked on a bunch of other companies, VMware mostly. At VMware, I actually did what was called Virtual Center, which was the management platform for building out ESX servers across a big data center. So that is actually somewhat similar to what we ended up doing here at Uber of managing our huge fleet of storage systems. And if any of you remember what your website is, it's pretty amazing. Alrighty, let me just sort of set the stage for this storage system. So I want to tell you a little bit about how Uber works. I assume you sort of know what Uber is, right? You install an app on your phone, you request a ride, and so forth. So on the top of our stack, of course, we have the cell phone app. And that basically talks to a layer we call the marketplace. So this is where we're matching riders with drivers. The marketplace system keeps track of all active trips that are going on at any given time. So it tracks all the GPS coordinates, it matches, finds the closest car, keeps track of the route, and so forth. And then when the driver clicks end trip, then it basically generates a JSON blob with all the GPS tracks, you know, who the rider was, who the driver was the search, and all kind of interesting information. There's like 20, 40 fields or something like that. And that basically get put into the back end of the system. And the back end of the system has to do, send an email with a receipt, has to charge a credit card, has to eventually put in some money into the driver's bank account, and so forth. It does a lot of fraud, and then those kind of things. All those data, all those trip histories, all those receipts, of course, has to be stored in some kind of storage system. And this is what we call operational storage. This is the storage that basically drives the whole thing. It has all the city definitions, all the user accounts, all the trips that has been done, and so forth. And that's what I'm going to talk about today. We also have a warehouse where everything gets into. It's sort of a big Hadoop, HDFS kind of thingy, where you can do all kind of queries. That's not the part that I'm going to talk about. I'm going to talk about the operational part. And the key thing about the operational part is that this is actually part of the online business, right? So when you are in the app and requesting, like, I want to see my past trip histories, I want to see my receipts, I want to look up my account, I want to change my phone number, and those kind of things. That's what is in the operational storage. Now, as most startups, you start out small and simple. So not very long ago, actually 2 years ago, everything was in a single Postgres database, pretty much. And of course, we had sort of scaled that up and bought a big machine and had a lot of SSDs and those kind of things. But it was sort of clear, this was early 2014, it was sort of clear that this is not going to work forever. Actually, it's probably not going to work by Halloween. If we don't do anything about this problem of scaling out our storage by January Halloween 2014, then Uber will basically stop working. So it's pretty clear now that we actually succeeded in solving this problem. We're still here, of course. But that was sort of the challenge we had. It's like, what do we do? And just sort of, when you can sort of look in hindsight of where we were, it's pretty easy to see that, this was definitely something we needed to do about. January 2014 is basically where that era was. And at that time, we actually didn't really do very many trips. Today, we do almost 50 times more trips than we did at that time, and that's only 2.5 years ago. So things are growing really, really fast. And since we have changed to the storage system I'm going to talk about, we've actually been able to scale to this sort of massive growth. We just did our 2 billionth trip in June this year. It was sort of a major milestone. Right now we do, just so for a sort of reference, about 5 million trips a week, which basically means that every second there's 60 people getting out of an Uber across the world. So it's fairly big. If you compared to Twitter, of course, it's very few, but this is actually real people moving around in the real world. Now, when you have to address this problem, right? So we have this Postgres database. You have millions of lines of code that basically access all these tables. We had hundreds plus tables to keep track of this whole system. So how do you sort of go about attacking that? You cannot just say, well, in 6 months we're going to rewrite the whole system and things will be good. So you have to sort of figure out where to attack it. So we did some analysis of the data we had in the Postgres database, and not too surprising. It turns out that trips is sort of the big thing, right? You know, this is basically what we do. We do a lot of trips. So 70% of the data was more or less trips in the Postgres database. So we decided to address this up front and say, well, this is the first problem we're going to attack by Halloween. And if we can get trips out of the Postgres data store, we'll be in good shape. It turns out that it was not just scale and latency and those kind of things that were a problem. It was actually also that making changes to a big relational database turned out to be sort of complicated. Sometimes when people needed a new index, let's say you need a new index on the trips table, the whole Postgres database will stall. And then everything stalls in the whole system. So we also wanted to have a system where developers very, very quickly could make changes to the data. It didn't have, and they could do it online without taking the system down. You know, this is sort of, you know, the system itself is sort of a ship that has left the harbor, right? You cannot stop it. It has to keep going. You can never turn it off. So everything we do to the system has to be done online. So very simply, that is sort of the world we want to get to at that point, and the world we are in now, where we still use Postgres and MySQL and other database technologies for various things, but sort of the main part is the schemaless system. The marketplace is actually run mostly on Cassandra and those kind of things. So there's sort of a bunch of different technologies in play. The system we have then ended up building now 2.5 years later, I have come up with is a fairly substantial system, I would say. It's not just storing trips. It's storing a lot of different databases for a lot of our services. It's installed across multiple data centers across the world. There's a huge amount of self-service and self-healing infrastructure. And I'm actually going to spend a little bit of time too talking about sort of the operational aspects of running a huge system that runs across thousands and thousands of hosts. So it's, I'm sort of thinking about installing a single database is easy, right? You know, once you want to have 300 databases across thousands of hosts, it sort of becomes very interesting. So a quick summary sort of the status, where we are. Today, about 80% of the data, particularly user accounts and trips, are stored in this system. We have gone from this single trips data store that we actually targeted back in 2014 to more than 300 data stores. And this is basically, think of these as separate tables or separate databases instances, if you will. Uber is a very microservice-oriented architecture, so basically services can get their own storage. And back in the days when we set up the first 48 machine cluster to run trips, you know, we thought that was huge. We have since revised sort of our idea of what is huge. But it's something that scales and grows. And again, if you looked at the graph, we basically double every 6 months, right? So things just sort of quickly gets bigger and bigger and bigger. Okay, so let's dive into a little bit about how the schemaless has been designed and is working. And as all systems, when you start up building a new system, you sort of look at, you know, how does it has to perform, you know, what kind of features should it have, what should the availability be, and so forth. The interesting thing, as you know, if you look at all these requirements, it's always a trade-off, right? You cannot just say, I want the perfect API, I want it to scale, you know, without any bounds. It has to be super efficient. It has to cost nothing, and so forth. So it's always sort of a trade-off, and particularly with storage systems, this is definitely a trade-off. You cannot just get full consistency and full availability and those kind of things. This is what, for example, the CAP theorem tells us. So there has to be some kind of trade-off, and you really have to figure out sort of what storage model does really work for your problem. And then the final part is sort of the time to market. At the time when we started doing this, we knew we had 6 months. So whatever we decided to do, it had to be done within 6 months. So you're not going to reinvent the world or spend 3 months sort of prototyping some idea. You actually want to have something rather simple, because you are going to run this in production. It has to work. So let me just quickly go through sort of the basic requirements we had when we designed the system. The first part was indexes. Indices was super important, as all the code that was running Uber was written to work against the Postgres database, and they are used to having indices. And there was lots of queries like, you know, the one that I show here on the right, where you're sort of looking up all the trips for a particular user in some kind of time range. The code here was written in, most of the code was written in Python using SQL Alchemy directly into the Postgres database. So in some sense, we were actually in good shape because people didn't write SQL statements itself. It was actually modeled using SQL Alchemy, which uses classes and so forth. So we could actually fairly easy, if we had the right abstraction, sort of change these classes inside the existing code, and then it will suddenly call into the schema system. The next requirement was on batch operation. So if you sort of think about how Uber works, right, is that people take a trip comes into the system, you have to bill it, you have to do payouts, you have to do some fraud detection, you have to do various kind of analytics, and then you just sort of sits there. So it's very much sort of computing in the front of data, or you can think of it sort of as a stream of data that is moving in that you sort of have to be processing. So we also wanted the trips data store to sort of support that model, that all these trips are sort of trickling in. We do a lot of computation on them. We ideally do it idempotently, so you don't get charged, you know, twice for the same trip, or worse, that we forget to pay out the driver. So we had to have sort of a robust system for processing all these trips, and then they sort of lay dormant. And this is actually very true. We have done some analysis where we sort of look at the access rate to trips, you know, after it's been taken, and you know, you can imagine it's sort of a curve that sort of goes like this. There's of course a little bit, people look up the trip histories, but you know, as opposed to Facebook, where people go in and look every time, you know, looking at past trip histories is not sort of a favorite pastime yet. So that was the second requirement. And then the last one. As I mentioned before, we are big into microservices. The Uber system actually consists of more than 1,000 microservices. Most of them are fairly simple. This is the idea with microservices. They call into other microservices to perform some kind of function. But a bunch of them, of course, have state, and then basically get their own local database. Or we call it data store, their own local data store. This can be a MySQL database, but it can also be a data store backed by schemaless, which is basically just scalable to whether you want to store trips, trip scale data, or similar stuff. So it's important to build a system where we sort of quickly can support this model of creating new data stores, tearing down data stores when a microservice dies, or sort of get decommissioned and replaced by other ones. And generally, this sort of microservice architecture is making it very agile to make stuff, right? Because we can easily add a new feature. We can easily take out a new feature. Take out a feature that is not needed anymore, has been replaced by a better implementation, as it's single microservices. And as each microservice has their own storage, it's sort of clear exactly, you know, what storage belongs to this. We can migrate it into a new data store if need be. And then, of course, the obvious one. You know, the data sort of has to be stored on disk somewhere. And this is sort of the crux of the problem of scale, because these disks are not really very big. You can maybe get a 2 terabyte or maybe a 16 terabyte if you're lucky. And then actually, this disk actually looks like this nowadays, just in case. It's just so kind of nice with the old ones. But you know, we want to store this across a lot of SSDs. And how many SSDs do you really need? Well, it doesn't take a lot of calculation to sort of figuring out that, let's say you have an SSD card with 2 terabytes. You stick 4 of those into a server, then you have a server with 8 terabyte. If you want to store a petabyte, which is sort of the scale we're looking at here, you know, 2 petabytes, you need at least 128 machines. And you cannot just store it on one machine, right? Because machines dies, racks dies, data centers goes off. So what we normally do is actually replicating data across 2 data centers, and we end up having 4 copies. So that means for a petabyte, you need 512 machines. So that's already very serious amount of machine and infrastructure you need that, and that's actually only a petabyte. You know, this is just sort of the tip of the iceberg of the scale that we eventually will get to here. You can ask why 8 terabyte? Why don't you just use a bigger machine? Of course you can do that, but the number still gets big. And then I'll talk about a little bit later why making that number bigger too has a different set of problems actually. The API that we did, and again, you sort of have, okay, what is trips? Trips is really just a stream of data coming in. All these trips are actually tracking real-life events that are happening out in the real world. And the nice thing about events is that they are sort of by definition immutable. You know, they happened, and this is what happened. And that is actually how we want to model our data inside Uber when we track trips, is that it's sort of a stream of changes that we track. So the way we designed this API, and also inspired by, for example, a big table from Google and other places, where it's just sort of a big column, sort of a table-style API, where you, for a given row, you can store a number of columns, and each column you can just store JSON blobs. So this is the schemaless aspect. You just store a random JSON blob. You can store whatever it is. The developers can change that JSON blob anytime they want to store something else. You don't have to make any table modifications to this. And then you can think of a trip coming in as like, here's the base information about a trip. You know, this is the rider driver. Here's the route. It's another column with the GPS points. Then there's some process that kicks in. It's like, based on this, I can compute the fare. Then it stores the fare. And we basically store all this information. So each row is sort of the entire sort of computation or history of one particular trip. And this is all immutable. So we have the whole track. We can go back and say, well, at this given time, you know, we computed this value for this field. And then this is very important because this is actually transactions or sort of business transactions that we are tracking. If you are familiar with the Lambda architecture, they very much advocate this model where you never overwrite data. You really want to keep all values in your database just in case, right? You could have code that accidentally overwrite your data, and then you are sort of in a bad place. So this is actually following this model. This also means that this is an append-only data store. Once you write a cell, you cannot overwrite it again. That value is there. You can write a new value in the same row and the same column, but with a different timestamp if you want to. And that's sort of how we track changes over time. It turns out that from a scalability perspective, this API also makes it very, very easy to scale, which is also nice. So how do we actually scale it? The physical layout of the database is that we take each of these rows. It is using UUID. The UUID, I just have a very short one here to get it to fit on the slide, but in practice it's 128-bit UUID. And we just do modulo 4K on that value and divide it, pre-shard it into a number of shards. And these shards are then co-located on a set of database clusters or MySQL clusters. So we didn't have to reinvent sort of a big storage technology. We basically take a rock-solid foundation MySQL. MySQL has support for basically replicating into slaves right across multiple, even across data centers and so forth. So we are reusing the async replication in MySQL. We are reusing all the query capabilities for indices and so forth from MySQL, and just have this in some sense, fairly thin sharding layer on top of my SQL to shard it out like this. And then we can actually run up to 4,000 clusters here if we want to, as we shard. But we start out with typically relatively few clusters, let's say 8 or 16 and so forth. And I'll talk a little bit about how we actually can expand this dynamically as we go. But the trick here again is that it's actually very, very simple. And very, very simple translate into robustness. And this is really what we're after. The next feature, which is sort of unique and actually hard to find in a lot of these scale-out solutions, is the efficient indices. And as I mentioned earlier, this is a key thing that we had to support to support the migration from the old code base to this one. And the idea with indices is that you basically specify an index. We see it here on the right, which is called the client index. And it basically says every time you write the column base, then take the field client ID and shard on that. And then store an entry based on that client ID. And this is what you see here on the left. If I do a put cell, now I'm putting a base column at, the UUID here is 100. And if let's assume we just have 4 shards as shown here. If you do 100 modulo 4, it's shard 0. So it will be stored on the 0 shard, right? Now, there's an index defined for the base column here. And then on the client ID, we take the client ID and also shard on that. And that means that we end up having an index entry on shard 2. And that's based on the client ID. And that has a reference then to the real cell or the real row, which is 100. And if you can see how this works, that let's say I'm client ID 10, and I take another trip. Well, my trip just gets random UUIDs, right? So they get distributed across all the shards. But my client ID ends up being the same. And since now the index is sharded on client ID, all the index entries ends up on the same shard. So if I now have to do a query to find all my trips, I know I can just do that on shard 2 and get all those UUIDs. I don't have to do a distributed query across all the clusters to find that. So it's very, very efficient indices. And in this particular case, we also included the fare. This is basically what we call a denormalized field, that I can very quickly get access to the fare too. So I don't have to sort of go back and pick it out on the original cells. The last feature is the ability to sort of process the trips as they come in. And this is also sort of very cool in the sense that as it's an append-only data store, that means it is really also just a log. And you can think of all the appends, if you order them by the time they're put in, it is just a long sequence of log. And we actually have an API that allows you to sort of look at, well, what happened in exactly this range? How did the database look in this time range? We can actually look that up. And we can use that if we just have some, we call them triggers, that sort of looks in the front of the database all the time, says, what happened? What got put in now? And then you basically just get a callback that says, somebody called in, put in a base column for this row. Somebody put in, a route column for this row, and so forth. So we can sort of tail the front of the database all the time. And this is what we use to drive all the back-end processing of all the flows. And there is one simple API call to basically do this. We call it Partition Read. You can sort of think it, sort of an analogy would be tail on a file. If you're on Unix, you can sort of tail everything that gets into the database. And then the triggers basically just sort of look at, there's a base column coming in. There's a route already exists for this row. I can compute fare. And then it computes fare and puts fares into the database. Then there's another tailer that says, there's base and there's a fare. I can do client billing. And we just sort of process it all. So by moving through all these shards in this way, we actually treat the database both as sort of the primary operational storage, but also as the sort of the queue of things that needs to get processed. And then we don't end up in this sort of, we have to store the information twice. It can get out of sync. Do we have to do 2-phase commits in 2 different systems and so forth? All that stuff is basically not needed, which is also translated into a simpler and more robust system. So that is sort of schema-less system, sort of the core database in a nutshell. And as you can see, it is a big table style API. So if you're used to something like that, well, I guess you're only if you work for Google, but that's sort of how it is. It's sort of a very standard API. It turns out that this API is applicable a lot of places. So we have written, it was originally designed to do the trips. We use it for a ton of stuff now. It turns out it just fits for a lot of places. And especially we are in a business where we are sort of tracking real life events. This is sort of what you want to do. You don't want to overwrite. You want to keep a log of everything that has happened. It's horizontal scalable by sharding, which you have to do in some way or another. And we can both scale the I/O and the capacity by adding more clusters. So, cool. Talk a little bit about availability. And once you get into operation, right, people will click on the app and want to write, and it sort of has to work all the time. So how does this system fare in the case of availability? And this is sort of where the rubber hits the road in some sense, right? That anybody can write a system, or you can buy some kind of thing. But no matter what kind of product you buy, whether it's something for the garden, or for the kitchen, or for your data center, that the difference is how does it hold up? Once you start stressing and when everything starts to fail, right? Does it suddenly just fall off a cliff for performance-wise, or does it suddenly start losing data and you cannot get it started for minutes and so forth? So this is clearly very important to us, that it's something that we have high confidence that is working all the time, and when it's not working, we can fix it very, very quickly. That is just super important. There's no time to call anyone when that happens. So let's look into a little bit about what happens actually. And the fundamental thing here, everything is in MySQL databases. So we basically have to make sure these MySQL databases are up. So this is where we spend a lot of time sort of worrying about keeping them up. Well, we don't really want to keep them up, but we want to make sure that when something bad happens to them, we can quickly recover, because they are going to die once in a while. Disks dies, host dies, racks dies, or they get misconfigured, or people accidentally turn them off, or you know what. So if a slave dies, it's not a big deal, right? We will still have the master, we still have a second slave, everything is fine. So life goes on. Slaves we really only have to recover in case the master goes down. So what happens if a master dies? Well, we have to sort of write to the SQL database. So if there is a trip coming in that has to write, for example, to that shard, how do what do we do about that write? And we really only have two options. Well, either we can fail and say, sorry, cannot write right now, you have to wait a little bit. And that is actually an okay answer for some cases, right? Because a bunch of the stuff that we do is batch processing, like sending out receipts and trips. So this is actually something that we can safely delay without sort of doing, too bad of a user experience in some sense. It doesn't mean that you cannot get it right. But the problem, of course, is that the caller wants this stuff to be persisted and replicated so we never lose it. So we actually have this, what we call buffered writes, or what, if you're used to Cassandra terminology, called hinted handoff, where, well, we'll just store it somewhere else, right? We have more than one cluster. We have 16, or we have maybe 128 clusters. So we can just store it in one of those clusters. So we just sort of put it aside and say, well, okay, it's fine, we'll take care of it. It's stored, it's replicated, we'll never lose it, but you cannot read it right now. You'll be able to read it later. That's sort of the guarantee we get. And the API is very simple. There's just the put cells, and you say, if you want this semantics, if you really want really high availability or really high durability, you just say, it's okay to buffer it. It's fine. I just need to get this stored. I don't need to read it right away. It's fine. And we do that when trips actually come down from the marketplace into the system. And the reason why this works is because all this processing exactly happened by triggers. Right, so people don't need to read this right away. The triggers doesn't need to know that this actually got put aside in sort of this hinted handoff table. Once it gets put back into the right place when the master is alive, the triggers runs and everything works flawlessly. So this is sort of the nice thing about an async programming model. Now, growth. What, as I said, we are growing every, basically doubling every 6 months. So what happens when these clusters get full? And this is also, in some sense, simple. I'll show a little bit picture of how simple it really was. But in principle, we just create a new cluster on the side. We'll set up MySQL replication, so all these 6 databases will have the same amount of data. And then now we have 2 duplicate setups. And then we can basically just tear them apart, so now they're separate with the same data. And then we'll just configure the distribution layer, say, well, half of the shard is on one side, or the other half is on the other side, and delete them. And then we're basically done what we call a split. So we can basically double the size of the whole system by doubling all the clusters at any point. And that is actually a fairly fast operation. So the key thing here is really to handle all these MySQL instances. So let me dive into a little bit about how we do this, and how fast is it actually possible to create a new MySQL database. And this is actually also interesting. You have these networks, right, on hosts, and you have disks on host. And if you want to get data into a host, you have to get it through the network. And if you have a 10 gigabit NIC on your host, the amount of data you can get into a host in an hour is about 3.6 terabyte. That's actually sort of the maximum. In practice, you can probably get much less in because you're using your network for other stuff too. And if a host dies, it typically has to be restored in less than 30 minutes. Ideally, much faster, right? So how do you deal with this? In the example I had before, there was 8 terabyte in disk space in each host, right? We have hosts that are much bigger, like with 100 terabytes and so forth. How can you actually restore that? And says, those 100 terabytes is going to take forever to get through the network to get that. The answer, of course, as it always is when you're writing storage system, is that you have to partition stuff. And the trick here is you don't have to think about the host. You have to think about the data. And you should think about the host just as a conduit for a bunch of data blocks. And what you want to restore is not the host. It's the data blocks. And you can restore those data blocks in parallel. If, let's say, there were 16 data blocks, which is all 512 gigabytes, then you can actually restore them in 30 minutes in parallel across a lot of hosts. So we actually have not only to partition the data across all the hosts, we also have to partition them within the host. So when a host dies, we can just restore the chunks in parallel in a lot of systems. And then we can actually, doesn't really matter how much disk host has. It just means that when something dies, we just have to have more parallelism in the case where we start up. So let me move into the operational at scale. So how do you start thinking about this, right? Because now an operation is not just about a host, right? It's suddenly like, if a host dies, I have to find 16 new hosts. I have to start things in parallel, 16 things. That doesn't happen sort of like by itself. And so this basically going to talk about this sort of red block. And I sort of think of the storage system is that you want to keep the storage system itself as minimal as possible. And then you want to have a side system, I would call it an outer shell or something like that, that knows how to manage this. And this is sort of a microservice architecture for storage services itself, right? That you don't want it as sort of one monolithic block, right? Because the operational system certainly have a tendency to have it's something you can update much quicker and with a lot less risk than sort of the core storage engine. So having this separated out makes a lot of sense in practice. And basically, once we operate this, let's say we have a few thousand hosts, we have multiple data centers, we have a lot of data stores. We basically want to be able to grow this, grow and grow and grow without having more people. For one reason is that, of course, it's much more cost-effective to have fewer people operating bigger systems. The bigger problem really is that you cannot hire more people fast enough. So in some sense, you just have to fix it. It is like people just don't exist. And the traditional way of dealing with this, and this is actually an actual screenshot of our first run book for doing a split. So this sort of, splitting things, I said, it's very easy. You just replicate and do stuff. In practice, you're actually doing this on real life, right? There's trips going on in this system, and you have to do this split. And if you do something bad there, something bad will happen in real life, right? So there was a long run book with a lot of checks and balances and so forth. And the problem with these run books is that people will not read them the same way, or they will forget something, or the phone will ring, or they will have to get coffee. Or if you read it at 4 o'clock at night, you'll read, he really didn't mean that. I'll skip that part. So it is just not scalable doing this kind of stuff. So basically, everything gets much harder with scale in some sense. And the typical things we hear all the time is like, well, a host fails, a rack fails, and all those kind of things. The biggest problem is really this drift thing. You have a big system with 4,000 hosts, let's say that. It just drifts if you don't keep track of it, because some of the hosts will have one version of the OS. Some hosts will have one version of MySQL. Then you have upgraded some of your operational agents and some of them. Then somebody has aged into some of the hosts and applied some commands inconsistently with some other place. Then there's some half-done operations somewhere else. And if you don't do something, it just ends up being complete chaos. And then thirdly, lastly, or separately in some senses, that once we did the trips data store, we were really deeply involved with the developers doing the trips data store, right? So we knew the access pattern, we could optimize the indices and so forth. But once you get into scale, when you have hundreds and hundreds of developers using these data stores, you really don't know what data they are storing in there. You don't know how to use the indices and so forth. So the tooling around troubleshooting performance, creating new indices and so forth just has to be much better. Right? Because they have to be able to do it themselves at scale. Otherwise, you cannot onboard all the developers in your organization to use this stuff. So this is also a side that we spend a lot of energy on. But I'll mostly focus on sort of the operational part and how you actually work with this sort of drift thing. And there are some famous slides. This is actually a slide I've stolen from I think actually a guy at Microsoft that I think back in 2012 he presented this pets versus cattle idea. And this is a picture of my daughter's rabbit, and it has a very good life. It's getting cared for. It's called Biscuit. And the thing about these things, like when you have your pets, it's like you care for them all the time. Even when they are not sick, you constantly go and check them. And it turns out that if you're a developer and have your little service, and you go into work every day, it's like, I'm just going to run a dtrace on it just to see if it's fine. Maybe there's something I can improve. That's how developers think too, right? When you have one, you have to sort of get into, at some point, into the cattle mode where it's like, I have a lot, right? And what matters is that I have a lot. It doesn't matter that I know all of them by name. And if some of them dies, I'll get another one, because what matters is that I have them all, right? And I want most of them to be healthy, of course. So what does this mean? How can you tell whether you're sort of in the pets mode or in the cattle world? And there are some very distinct signs that you can sort of see in your organization. If you're in the pets world, then there is some developer in your organization that you can go and ask. He would know everything about the system. And if he's not there, nobody would know. That's sort of the thing. All the changes is something about logging into machines, running some big run books if you're lucky. Otherwise, he just knows what commands to run on all the things. And the most telling one, and this is definitely true, is that somebody knows how to do these commands, and he is immensely cool, right? Because he is sort of the magician that knows all the Unix commands that will fix stuff. And this is how all organizations work. Right? I'm pretty sure you have all been there or are there to a certain extent. And this is where it has to start. When it's small, it's easy to do this kind of thing. But as you scale, you sort of have to get out of this, that you really want to move to a world where you describe what you want. You actually don't really care whether a database is on one host or the other. All you care about is that this cluster exists and it has 3 slaves, and put it wherever you want. And this is what we call goal state. And this means that this whole notion of having these experts that knows all the commands is sort of like a non-event. You actually don't want any experts. You want all your developers to start writing code that makes the business better, and the system just do it itself, right? It's like, this is what we do. So some examples of goal state. Goal state is really about sort of describing what you want in a way that the system itself can remediate it. So a non-storage analogy is that, well, if you have a service, you tell the system, I need to run this service, I need to have 5 instances. Then the system knows that you need 5 instances. The alternative is that you go in and say, deploy an instance on machine X, deploy an instance on machine Y, deploy an instance on machine T or something like that. The problem is, if you have specified in that way to the system, then if one of these machines goes down, then the system has no idea what to do. It's like, well, machine T died. I don't know, do you want 3 instances, do you want 5 instances, you start again, has no idea. So you want to move to a model where you can describe what it does, so in case something fails, you can automatically remediate. If you take a look at these ones from the bottom, then you can see, I just described to the system, I need instance X. Then the system says, I need to create an instance. Okay, it needs some clusters. That's sort of the second one, so I run the clusters. Well, a cluster needs a master database, so I'll create a master database. Then another rule kicks in and says, well, all masters should have slaves, so it adds slaves, and so forth. If a slave dies, a rule kicks in and says, there is a slave missing for this one, I'll create another one. If a host dies, a bunch of slaves will be missing somewhere, the system can just go in and create it. This might sound a little complicated, but there is actually a fairly simple pattern that we use all the time, which is this, on how to basically deal with these goal state system. And the idea is that the operator never works directly on anything. He just goes in and changes the model, describing what he wants. This is sort of the goal state on the top here with the green arrow. And we constantly go in and monitor what is the exact state of the system at any given point. And we put that into the actual state. Then we basically run a diff. In some sense, we can report on the drift, on the diff, which is actually a report on the drift. How different is the real system from the desired state. And then we can basically have rules that says, well, based on these drifts, I'll kick off some workflows to go and remediate it. And this is a continuous process that runs and runs and runs, right? So we constantly keep track of any kind of drift, whether it's simple stuff like, the OS is different versions, or maybe it's just saying that, well, this OS has run too long. We want to reboot all our machines every 14 days. So we'll just go and do that, and we can ensure that the entire fleet is done. And as a developer, this is just something that runs all the time. So, okay. In some sense, it's a very, very simple pattern, but it's super powerful. So a very simple example of where we use goal state, we actually use this in several levels. We use it at the top level where we're talking about databases and clusters, but we push it all the way down into the host. So when we have to start, we run multiple MySQL servers on each host because of this sort of chunking we have to do for restore. We actually have an agent on each host. And that agent, and as agents are, they are supposed to be active entities, right? So that agent basically runs this goal state loop. And it goes in up to the management software, which we call opsless, and pulls, what is my desired state? And then it goes and does local, basically PSs or Docker PS or stuff like that to figure out what is actually running on that host. And it ensures that all the processes on this host matches the goal state. It's the only thing it does. And then it also reports on the actual state all the time. So this means that when we make a change to the goal state, it sort of automatically gets pulled into all the machines. And if you're making a change and a machine is down, it's okay. It's down for a little while, or the network is down, or maybe it's partitioned or whatever. At some point it comes up, and these machines will come back up and pull the state and basically get them back into where they're supposed to be. This is super scalable too, right? Because we don't have one process that has to sort of manage thousands of hosts across all databases. This is a big distributed system running across the whole thing. So a very simple example. let's assume we have sort of two hosts here with a master and a slave in a MySQL. And this is basically set up in this table saying that, foo DB1 should be a master, foo DB2 should be a slave. Let's say I want to do a slave promotion. You can imagine if you've done that with MySQL, it's executing all kind of weird commands everywhere. You have to wait for replication lag to go down and so forth. What we do is basically just changing this goal state. And then we sit back or get coffee somewhere. And once you change this goal state, right, we just have to wait for the optless agents to basically pull this state. This is happening async, so they could pull it in any. It could get to one of the hosts first, and let's just say it gets to the right one first. This one says that, well, it knows, the agent knows that, well, I'm a slave. In order to transition to a master, I have to have all the latest data. I can only ensure that I have the latest data if the one I'm replicating for is read-only. So it's basically sitting there waiting, but the active loop actually happens all the way out on the host, right? So there's very little latency in this loop. And then once the data propagates into the other host where it says, I'm supposed to get idle, I'm not supposed to be a master, it basically means that it goes into read-only mode. Then the other agent figures that out, say, now the ones I'm slaving from now has stopped being a master. It's read-only, my replication lag has gone to 0, I'll become a master. And then you suddenly do this. Very, very simple. Two very simple state machines running on two different machines with very little coordination. And of course, this is all driven through a nice UI where we have tons of workflows where we can just do this. This is sort of phase one, because the ideal thing is, of course, why do anybody has to click a button? And this is actually what we're moving into right now, is that these slave promotion, of course, has to happen really, really quickly. So we're actually moving away from using MySQL replication, and the MySQL host is run in a RAF cluster. So we basically have a process in front of that selects who is the master and then replicates all the writes using a consensus protocol to the different databases. And that means that if database becomes unavailable, maybe even temporary, it automatically does the master election in less than 100 milliseconds. Which is actually fast enough that for most clients they wouldn't notice. They'll most, of course, increase in the lag, but we do retries. And then it's completely transparent. So this is also a way of sort of pushing this sort of goal state down there, saying that, well, now the RAF consensus protocol is just make sure your goal state is just to ensure that one of them is writable, and you handle this. So this is actually the end, and I think I'm also about out of time, right? Very, very quick tour of some of the highlights of this schemaless storage systems. The takeaway here is, one thing is the API, another thing is the operational part. And when you're doing sort of an online business, the operational part is super important. You really, you develop on it all the time, but you also keep it running all the time. So you spend a lot of your energy there. And making stuff sort of easy to operate at scale is not a trivial effort. We have spent a serious amount of engineering resources on this, but this is really what makes it scale. So it is super important stuff to do. So finally, we do have a blog in case you found this interesting. A lot of this stuff that I've talked about, the schema list, migration and stuff like that, there's tons of blog posts on that on our blog. I have even written one of them. And a part of the team up here has written a bunch of them. So go and see them. There's also a bunch of other different stuff that we do. And I think that's it. And we might have time for a single question, maybe.
You talked a little bit about where you're going, but maybe more you can talk about seeing schemaless and Uber storage in the next 2 years and beyond.
Right. So where it's going. So clearly we are growing and growing and growing, and storage is very tricky, right? So in some sense, this system is sort of the first generation of what we've got, and I think where we're going in the future is there's a bunch of different directions. One of the things, and most of it is really about ensuring that we have the right APIs that makes it easy to develop services. And one of areas where I see where we can improve where we are today is how do you deal with data that is partitioned across multiple data centers? We have various solutions today, but I think we can come up with better ones. There is definitely areas where you want better transactional support or some kind of isolation and multiple updates. So this is also what we're looking into. But we're actually spending quite a lot of time thinking about sort of what are the perfect APIs. Because while the big table API is sort of is very flexible, sometimes you want some high-level abstractions. And then is definitely the cross data center reliability is a big focus for us. Anything else?
Mind sticking around? We could do one more question.
Mm-hmm.
Is that cool? Heads on. So what about, can you elaborate on how you ensure that data is written completely with all indices when they are on separate hosts and no transaction covers the whole update?
Right, so the question is about indices. How do we ensure that they actually update the consistency? And we actually don't. So they are secondary indices, and they are eventually consistent. So we don't guarantee that they are updated at the same time as the primary cell is written. So typically they will be. So we definitely try to do that. But if that database is down, that chart is down where the index is hitting, that will just sort of be put aside also in sort of hinted handoff and applied later. So the secondary indices are eventually consistent. This is one of the things that we're actually looking for in the future, to think about making them consistent.
Awesome. Thank you.
Right, thanks.